Hi everyone, I'm Chen Chen. Thanks for listening my presentation. Today I will present my work on machine learning cloud APIs used correctly. We have released a benchmark and code through the below link. Machine learning provides effective solutions for a number of problem domains, including some critical ones. However, developing machine learning software requires cross-domain knowledge. Developers face many problems, and these problems will lead to severe bugs. Under such scenario, service providers like Microsoft, Google, and Amazon provide machine learning cloud APIs in a form of function as a service. Such APIs enable developers to easily incorporate learning solutions into software systems. It requires less domain knowledge and completely removes developers' burden of designing and training neural networks. Because of these benefits, more and more developers adopt such APIs. There are more than 35,000 open source projects on GitHub that using these APIs. 14,000 of them are created in the recent 12 months. It sounds like these machine learning APIs are perfect, right? But actually, no. Many developers did not realize that these machine learning APIs are different from the traditional ones. They perform cognitive tasks whose behavior are very likely to be misunderstood. How people ask questions greatly affects the result. For example, what's in the image and which food in image will lead to very different answers of the same image. In addition, how API perform is heavily affected by the training data, whose property may not be known to the API users. Their output are typically high-dimensional numeric vectors, and hence may be tricky to interpret it. Finally, they also introduce complicated accuracy and performance trade-offs. As a result, it brings up new types of ML-specific bugs, which are not addressed by the traditional software testing. We will introduce these ML-specific bugs in the later slides. In this work, we perform an empirical study of the latest versions of 360 GitHub projects that include non-trivial use of ML Cloud APIs. We identified 481 misuses from 249 applications. In addition, we designed several checkers and tools that automatically search and handle common errors. Let's first introduce the empirical study. For manual studies, we collect a suite of 360 non-trivial applications that use Google, Amazon ML APIs. Since there are many toy examples on GitHub, we manually confirm they each target a concrete real-world problem. This application includes 3 major ML domains: vision, language, and speech. The median age of them is 18 months. 40% of them has more than 10,000 lines of code. Because of the young ages of ML API services, we must discover API misuses unknown to developers by ourselves. Our team manually examines every use of an ML API for potential misuses. For every suspected misuse, we design test cases and run the corresponding application or its component to see if the misuse truly leads to incorrectness or inefficiency comparing with our fix. During this process, we report representative misuses to corresponding application developers, receiving confirmation for many cases. Through empirical study, we identified more than 400 API misuses in our benchmark. Our study found that the misuses of ML APIs are widespread and severe. 69% of applications contain misuses in their latest versions, more than half of which contain more than one misuse. We have summarized 8 misuse patterns. I will introduce some of them in the following slides. The first misuse pattern is called Lindarang API. It is caused by the challenge of cognitive semantics. Unlike traditional ones, ML APIs are trained to recognize real-world data, emulating human behaviors. Because of this complicated semantic, some ML tasks have functional overlap. Therefore, even the developers use the wrong API, it may not be revealed through testing. For example, these 2 APIs both offer description tags for the input image. Image classification offers tags for the whole image, answering what is in the image. Object detection outputs one tag for every object in the image, answering which food are in the image. Let's look at a concrete example. What's in your fridge is a smart fridge application. It takes photo from inside the fridge, uses ML API to process photo, and recommends recipe based on it. The API uses to process image is Google image classification. Is this the right API to use? If we test it with this photo, the API will output food, egg, and box, and a meaningful recipe will return by the application. It looks good. However, if we try a different photo, as you can see here, the output is not accurate enough to provide meaningful recipe. This API only notices images about food and vegetable. This is useless in generating recipe. Developer might think Google API is just not good enough. But actually, there's a bug in the software. Applications should have used object detection. This API outputs tags for each individual object. Now we are able to recommend a dish of mashed carrot and potatoes. This is not the only application. Many developers meet troubles in choosing image classification and object detection API. In fact, 99% applications using these APIs pick the wrong one. In addition to the cognitive task, the semantic of ML API is also defined by training dataset. While the difference seems subtle to developers, it greatly affects the inference accuracy. For example, there are two image-to-text APIs, text detection and document text detection. They can both extract text from an image, but one is trained for work on painting text and the other is for the handwritten text. Unfortunately, many developers do not have the domain knowledge and misuse them. Notex is an application designed to extract handwritten notes from photos and organize them to a digital notebook. The developer wrongly used text detection. As a result, the quality of output node is very poor, as you can see here. Again, this problem will likely escape traditional software testing, as the developer and user likely just think that ML API is not smart enough. They don't realize that by simply switching to a different API, the quality of output would be much better. Actually, there are many other applications facing the same problem. 11% applications using these APIs picked the wrong one. There are also other APIs that developers frequently misuse. Please refer our paper for more details. Due to the challenge of numeric vector outputs, many developers misinterpret ML API outputs, especially in sentiment detection API. Take text as input. This API returns two float numbers as shown in the plot. X-axis is the magnitude, referring how strong the emotion is. Y-axis is score, referring how likely the text is positive or negative. We can see that the interpretation is very complicated. Let's look at this diary application, Journal Box. It takes feedback to user based on their emotion expressed in the diary. The developer wrongly parsed the API output, is thinking a mixed feeling diary as strong negative, and thus give a wrong response. This problem troubles a lot of developers. More than one-third applications using this API make a mistake. Because of the complicated accuracy performance trade-offs, around 80% application misuses asynchronous APIs. Different from many labs where asynchronous APIs are usually used for improving performance. In AML APIs, asynchronous ones are offered for long inputs, but its performance is really bad. Unfortunately, programmers usually do not realize this performance difference. They often misuse asynchronous APIs and cause unnecessary, huge performance loss. The complicated trade-off also leads to another kind of misuse, unnecessarily high-resolution inputs. Around 90% applications using Vision APIs meet this problem. Vision API accepts inputs with a range of resolutions. With higher resolution, the performance degrades greatly, while the inference accuracy saturates quickly. Many developers do not understand the trade-offs and feed the application with unnecessarily high-resolution inputs, causing huge performance loss. Overall, we find 8 types of misuses. They are caused by the nature of learning itself, complicated requirements, cognitive semantic, and complicated trade-off. These misuses lead to various types of problems, including reduced functionality, degraded performance, or increased cost. Please check our paper for the detailed discussion of all these anti-patterns. Overall, around 70% applications in our benchmark suffer at least one misuse. Guided by our study, we designed checkers that automatically detected more than 1,000 misuses in a much broader set of applications. For 3 types of misuses, we also designed API wrappers to help avoid the other 4 types of misuses. In conclusion, we found that the misuse of machine APIs is widely existing in software. In this work, we build tools to automatically tackle some of these misuse problems, but there are still many unsolved problems. We welcome people to try our benchmarks and tools and join us in tackling misuses of machine learning APIs.
Good afternoon again. I hope that I'm sure that you enjoyed the presentation by Chen Cheng. We have here Chen Cheng and Si Cheng Liu, two of the authors of the papers entitled "Are Machine Learning Cloud APIs Used Correctly?" This is the second technical track paper we have, and they conclude this section. I hope that you have enjoyed the pre-recorded video. So there is some icebreaker in the audience, someone that would like to start the discussion of this important piece of research. There is someone? No questions? Okay, no problem. I have a couple of questions for our authors. My first question concern generalizability of the results, or if you prefer external validity. So in your research, you focused on machine learning APIs offered by Google's and Amazon Web Services. Do you believe that the observed results can be applied to APIs offered by other service providers? You only study open source project hosted on GitHub. So my second question is related. My second related question is: do you believe that the observed results met also for commercial projects?
Yeah. So we believe that our result is general to all machine learning APIs. So actually, so when we are doing the study, we've checked also the Microsoft API and find that they actually share the same similar functionality. But just due to the limited number of their open source applications, we do not include them in our benchmark suite. Yeah. And in terms of the why we are only checking the open source ones, because that's the only one that we could get it from it. So we believe this is the best we could do to get an broad and variety of applications. And we believe for the commercial ones, there would be have the similar behavior. And yeah, and we encourage all the researchers to also participate in this project, and we have open sourced our benchmark suite.
Yeah, I understand. It is very difficult to have the participation of researchers from the industry. So I understand that one of the limitation that you mentioned correctly in your paper about the kind of projects is difficult to deal with. Okay. We have a question from the audience. First one, the question is by Raya Bahadur, that congratulate with you. So great talk. And the question is, do you have recommendation of how to avoid these misuse patterns, like how to know the right image resolution to use?
Yeah. So actually, so for those cloud APIs, they have a recommended resolution, and some of them are 400 times 600, around this size. But in terms of object detection, then if it's actually related to the size of the object. So if you believe that the object occupies a large portion of the input image, then you can decrease the resolution more. Yeah.
Okay, we have another interesting question from the audience, and this question comes from Cristel Hurtado. That again congratulate with you, and she wrote, "Thanks for your very interesting talk." Another kudos from the audience. It is the second one. Despite using an analyzer to detect ML API misuse, do you have any recommendation to provide feedback and train developers to decrease the number of API misuse? So the question is about the practical implication from your research. What are the most actionable results from your research, and how these results could be used from practitioners?
Yeah, thanks for the question. So our research has already summarized 8 different misuse patterns, and also in our artifact we provide some examples to trigger these mistakes. We hope this information could help the developers to reduce the misuses. And about the feedback and training steps, I think it is our next step to do so.
Okay. So my question could be related to future work that is mostly related with the answer you provided to the last question. What do you believe that it is the most important future work for your research? And do you expect something of interesting? What do you expect from these further research on this important topic?
Yeah, so usually after a bug study, then the next step is the auto detection and auto fixing. So my future research plan is that I can automatically detect these misuses and also provide the solutions to fix them.
So, do you have some idea or on how to automatically solve this task?
Uh, yeah, so we can just take the calling the run API this misuse as an example. So when the developers misuse these APIs, so I can maybe I can provide some test cases to tell people that your program uh, will be run on these inputs, and also will recommend them to use the correct API.
Okay. I have finished the question on my part, so I hope that there is someone from the audience that can ask. Okay, we have a question from Fabio Marcos. Thank you for the presentation. Are you moving to provide some possible correction? How will be the accuracy in this case? Your expectations?
Yeah, so for my future work, I'm planning to provide some possible corrections for the misuses. And how will be the accuracy in this case? I guess it definitely cannot be the 99% accuracy. I think it might be around 80%. So because it is hard to infer the application scenario just by the code analysis. So maybe for some applications, they are frequently maybe working on a camera, or some are working on some uh, user drawn figures. So then in these two different cases, their input is very different, and they may need to use different API to solve them. But by just analyzing their code bases, it is hard for us to trigger that. So we will provide the fixing suggestions and let the developers to make decision whether they want to accept it or not.
Thank you, Chen Cheng. We have more or less 30 seconds to spend together. So if you have a very quick, actually a very short question. We have a question, but I don't think that we have enough time to answer that question. After this talk, we will project it in a discussion room. So, Long Zhang, can you discuss with you during a virtual coffee about the question that you can see on the. Thank you all